Our next speaker is Honza Král, and he's going to talk about how to make sense of big data using Elasticsearch. He's a Python developer and one of the core contributors to Django. So let's welcome Honza.
Thank you. So hello. As it's been said, my name is Honza Král, and I actually work for the company behind Elasticsearch. It's a startup that provides support and training in case you ever need one. So let's get started with what actually Elasticsearch is, or what it tries to do. My goal in this talk would be to explain a little bit what it can do and show you how it is done behind the scenes, so you can sort of judge for yourself what it would be good for and where you would probably use something else instead or in addition. So what Elasticsearch actually is a distributed search engine. So if we take it word by word, it's distributed, which means that it's actually fully clustered. If you download Elasticsearch and you run it, it's a very easy process. All you need is have Java installed, and then it will start automatically. And you run it twice, the two instances will find each other and they'll form a cluster and they'll start sharing data. That's really all that is required. So as long as they're on the same network, by default, they'll start talking to each other. It's a very good way how to steal data from others on conferences. Just open your notebook with your Elasticsearch running with the default configuration, and you will get half of the data from everybody else who has the same configuration. So this is very good for development, and it allows you to get up and running very quickly and sort of play with it, but it's really not recommended in production for obvious reasons. So make sure to be aware of that. Other than distributed, it's an open source product. It's Apache license, so there's no problems there. It's document based. It uses Lucene as its engine, as its core, sort of to do most of the heavy lifting, the indexing, and some of the storage. And it uses HTTP and JSON for pretty much everything that it does. So it's very flexible. So it's document based. So it can index and work with anything that you can express as a JSON document. The JSON document can be nested, so you can have documents within documents or JSON objects within JSON objects. You can have lists and everything. It's not exactly schema-less, but it has dynamic schema. So you don't have to define the schema before you start putting data in. We will sort of infer the type from the data as we see it. So the first time that we see a field that we haven't seen before or we haven't been informed previously what it should be, we look at it and we take a guess. Does this look like a number? Does this look like a date? If so, we will annotate it properly. If not, the fallback is always a string. It does support some relationships between documents. It's not isolated only to work on a single document. The two types of relationships are nested and parent-child. Nested is for the situation where you have inner objects that should have citizenship status on their own. For example, if you have a blog post and comments. So you're going to search on the comments maybe, but they're still part of the blog post. The parent-child relationship is then for more independent documents that are not part of one document but have some one-to-many relationship. For example, I'll be using Stack Overflow for some of my demos. I use the question and the answers on Stack Overflow to model the parent-child relationship. So the question is the parent, and then the answers are the children. So you can query for questions by specifying what the answer should be. So this is what an example document would look like. It's, as I said, any JSON document. This is a real-life question from Stack Overflow. Stack Overflow is very nice that it provides all the data for download. with a Creative Commons license, I believe. So you can see the classical suspects like title and body. You also see the comments, which are, in this case, would be the nested documents. And you can immediately see that we can support both individual values as well as arrays and lists and inner objects. In fact, there is actually no distinction for us whether a field has a single value or multiple values. You can use them sort of interchangeably. So that's sort of the document model or the data model. So what can you do with the data once you have them in Elasticsearch? Well, the first answer is sort of obvious, right? If a product is called Elasticsearch, probably it will do search. And it actually does. The more interesting part is the unstructured search, the full text search, where we can actually take text in individual fields or across all fields and do a proper full text searching. So we can do everything from stemming and all this complicated stuff. So if you have basically anything that you would expect from a full text search engine, we can do phrase searches, we can do fuzzy searches. We have a scan API if you want to actually access all the data that were a result of a query. That's sort of the first use case. How many of the data science people would use Elasticsearch is they would use the query API and the search API to limit the result set, to limit the data set, and then unload it all from Elasticsearch. So let's say that you have 100 terabyte of data that you want to process, but you're only interested in always in some chunk of the data. Elasticsearch then will provide you with the functionality of defining the criteria for the subset that you're interested in, and just loading it all into memory or into Python and do with it whatever, some more complicated analysis that Elasticsearch is not equipped to deal with. So the full text search actually relies heavily on analysis, which is a process of the text coming in, and we need to analyze it sort of to make it into a canonical format that we can then search on. This analysis process includes simple things like lowercasing and also fairly complicated things like stemming. And it essentially boils down to we have a text on the input and a list of tokens on the output. And while this is a problem that's fairly easy and well understood, for example, for English or for most European languages, it's something that's very difficult, for example, for a lot of the Asian languages that don't necessarily even have white space. So how do you even split it into words? How do you deal with things being typed in different script? So this is all something that Lucene has covered, and we sort of tap into that to make that happen. So that's one type of the search, the more interesting one, but also more esoteric. The other one that we are all probably more familiar with is a structured search or filtering in Elasticsearch. Those are for exact matches, ranges, geofilters, and everything. And while a query will give you not only the documents that match, but also information how well the documents match. So for example, this document matches very well because it has the search term in the title and also in the body. Filters will do none of those things. It will just limit the result set. And because they're much simpler, they're also much faster, and because of the underlying implementation, they're actually cacheable. The way this works internally is after a filter gets evaluated, so we get a list of documents that would match a filter, we essentially store this information in form of a bit set. So a bit set is really what it sounds like. It's 1 bit per document, because we store documents in a predictable fashion and we never change the order. We can address them just by using a position in a bit set. So we can very easily have a data structure that's super small, like 1 bit per document. How more efficient can you get? and super easy to work with. For example, if you want to combine multiple filters and you have 2 bit sets, that's a bitwise operation. That's something, probably the most effective operation you can do on a CPU. So it's very nice for these reasons, and this also enables us to cache individual core filters, so the individual conditions, and then always combine them together from the caches. So if you have 10 filters in your query, and only one of them keeps changing, you will always reuse the 9 remaining caches. So this is something that makes our filtering very fast and very efficient. We'll see hopefully examples later if we don't run out of time. So the last thing that we can do as part of sort of a search is we have a bunch of tools that we call suggesters. I separated them into 2 groups. One is a terms or a phrase suggester, and that's the functionality that everybody knows by the "did you mean?" If you type something into Google and you make a typo or it's not as common, Google will try to suggest you something. And that's what term or phrase suggester is. The difference between those two is the context awareness. Whereas a term suggester can find typos in individual words. Phrase suggester can even find correction in phrases where all the words are correctly typed, but don't match, don't make sense together. My favorite example for this, if you try to search for Johnny Walker, the whiskey, and you specify Johnny as Johnnny, you won't find anything, because with the whiskey, Johnny is actually spelled with an IE at the end. So term spell checker will not find it because it's still a correct version of how you can spell Johnny. But a phrase suggester will actually catch it and say, hey, did you actually mean the whiskey? So those are the phrase suggesters. And the completion suggester is something for autocomplete. It's super fast because it was designed that it should be executed on a simple keystroke. So whenever a user is typing something in, you can keep running the autocomplete suggester and ask every single time for autocompletion. In this case, fast for us means sub-millisecond response times. So you can literally do the completion on each keystroke to help people facilitate this. The only, I'm not sure whether it's a downside, but it's certainly an important characteristic, is you need to supply the score yourself. Because we are not able to say, like, on this one letter, how well does this word match? That's an information that has no meaning. So you need to rate the possible suggestions manually, basically based on your business logic. So this is what we can do in terms of searching and filtering. We support all ranges of operation, like ranges, matches, exact matches, fuzzy matches, geo matches, so you can limit something to an area or something like that. And now let's look a little bit on how it's implemented. So a full-text search, or searching through information, is a fairly old problem. It was first solved in the 13th century. It's one of the oldest data structures out there. And the data structure is called an inverted index. You're all very familiar with this because whenever you read any sort of scientific book or anything, at the end there was an index. That's exactly this. It's a list of terms with pointers to documents in which they appear with some metadata. In case of a book, it's a list of terms sorted alphabetically with a set of pages where those terms occur. So this is an example of one such inverted index. You can see that we've indexed 4 files, file 1 through 4, that deal with Django, Flask, some jazz music in there, and we've essentially found all the words in the document, sorted them, and then for each we have a list of files in which they occur, again sorted. So now when we actually want to execute a search, so let's say that we want to search for Python and Django. That's super easy. We just locate the two words on the left. And we have two sorted lists that we now have to merge. So we just walk those two lists, and whenever we see the same document, that's our result. So as you can see, it's a very effective mechanism because it's just merging sorted lists. And it has one other important characteristic, is it's not limited to just using one index. You can very easily get these lists from multiple indices at the same time. In fact, that's how it always works, because this data structure, while it's pretty straightforward to build, it's super hard to actually update. So most of the search engines don't update. They'll just create a set of inverted indices like that, and then when they query, they will query across them all. At that point, it's just one more step to make it distributed over a network. So you can immediately see that you can get the sorted lists from as many indices as you can, which means that when you search with Elasticsearch or when you filter, you're always only hitting the index, and you're hitting an index on every single field that you're querying. There is no such thing as a full table scan. We never actually go to the document. So that's something to keep in mind. That's, again, one little trick that keeps us fairly optimal. And of course, this is a data structure that lends itself to a lot of improvement. For example, if we just mark the positions of the words in the files as part of this list, we can now do a phrase search. Because if we are searching for the phrase Python web, it means that we're looking for a file where the word Python is followed by the word web. So during the merging of these two lists, we just need to look at the positions and detect when there is an offset of 1. That's a phrase. That means that in that document there was the word Python followed by the word web. And we can very easily make this more flexible. We can say, for example, that we allow 2 or 3 words to be in between those. And so instead of just looking for a difference of 1, we can be looking for a difference of less than 3. So again, a very, very powerful concept, and everything just works because we are, in the end, just merging sorted lists, which is a very effective operation, an operation that that lends itself very well to distribution, both in terms of CPUs and in terms of network. So it's easily distributable, and it's also very flexible. Again, because of the fact that I can query across multiple indices at the same time, I have a lot of freedom in how do I structure my data, how do I manage them. For example, I can have an index per day, which makes everything manageable. Like one day worth of data is usually fairly manageable, and typically I'm only interested in today. And then nothing is stopping me to actually query across the entire week. I'll just query across 7 indices. I don't care. There is no penalty for searching across indices. So that's really a really powerful schema that you can use to store a lot of data in Elasticsearch. That's one of the reasons why Elasticsearch is very popular for storing log data. When, either machine logs or any other logs. Log is essentially anything with a timestamp. So you can use this to store indices, to store data every day, and then you just delete the old ones, or remove them, or archive them, or backup them, and you can keep going forwards, and you can grow every day. So this was searching and how to actually get the data that you want. And that's really great if you already know what you're looking for, if you just want to limit something. But this talk has been about exploration, or should have been. It hasn't until now. So let's deal with that a little bit more. So what I want to talk about now is aggregations. Aggregations is essentially any operation where you take a group of documents and you run some calculation on them. We just use the terminology of metrics and buckets. First, we define different buckets into which we divide the documents that we have, and then inside each bucket we run a metric. So buckets can be nested, so you can create a bucket per year, and then inside each year you can create a bucket for each category, or buckets based on range from central London. So something like that. And the metrics are then the usual suspects, like numerical aggregations and statistical ones, and also some interesting language things that we'll see later. So some examples of how you can define buckets in Elasticsearch. The first one I've already mentioned. You can create a bucket per category or per range on a numerical field. You can use geodata to actually do the same thing. So do a range based on distance from a central location, or just create a grid into which you want to divide your documents. You can do a date histogram, so you can have daily buckets or monthly, and general things like that. Nothing too surprising. The only important thing to keep in mind is that you can nest those. So you can create multi-dimensional aggregations in a single query. That's a very powerful concept that takes a lot of people a while to wrap their heads around. So, and then the metrics that go inside, there are some very simple ones like count, which you will actually always get. You don't need to specify that. Sum, average on a numerical field, or even minimum on a string field. Why not? You can do stats or extended stats, which will give you the basic statistical indicators like standard deviation, sum of all squares, and all this stuff that I don't really understand. And also, we have some very interesting aggregations. One of them is significant terms. It will actually take all the terms, all the tokens, all the words from a field, and it will give you the ones that are specific or significant for that bucket. So what's a specific tag for a certain category or for a certain time period? In other words, what's trending? So you can actually see immediately like what was specific for this bucket. So for this week, what was the most commonly used tag compared to all the others, not just in absolute values, but comparatively to other buckets. And of course, you can mix and match those. So you can nest the buckets, then create define multiple metrics on any of the levels, and you can go as deep as your memory will allow. This is all calculated in one pass over the data in near real time. By near real time, I mean milliseconds. We'll see some examples later. So it's tens of milliseconds on reasonable hardware. This scales actually pretty well. We have people running this on datasets in the size of tens and hundreds of terabytes. So how is this implemented? We've seen the inverted index, and that's really not a good data structure for this. So for this, we actually have a different one. We take the inverted index and we uninvert it. So it's the field data structure, and we call it the uninverted inverted index, because that's always fun to say. And there are two different ways how you can actually use those. By default, we will just when you first need this data structure, we'll uninvert the index and load it all into memory. And that's obviously very fast once you have it in memory, but it obviously eats a lot of memory. There is another option that's been added recently to Elasticsearch, which we call doc values, and those actually reside on disk. So they're built at index time and are updated as you index more documents or change the existing ones. And it's almost as fast as the in-memory ones. We're still working on making it even faster. Currently, in master branch, we can get it up to 40% slower. That's the worst case scenario that we have seen so far. Usually, we are about the same as the in-memory ones, and in some rare cases, even faster. So exciting, we are getting really, really fast. And this is obviously not our invention. This is not something specific to Elasticsearch. This is how all column stores actually work. Just store the column together so that you can iterate very quickly over all the values for a certain field for aggregations. So in this case, we are very similar to any other data store that's geared towards aggregations and analytics. So now we have all the tools. We know how to limit our data set if we know how we are limiting it. We also know how to ask Elasticsearch actually to give us all the possible limiting values just by using aggregations. So that's the exploration part. So now let's see how this typically fits together. I've prepared 3 examples, 2 of them simple, and the third one will actually be live coding, so fingers crossed. So the first example, the most commonly associated with search and with this type of thing, is faceted navigation. When you search a website, let's say a website designed to actually store code, and you do a search, and I'm using this example because, yes, GitHub is actually using Elasticsearch for that. And you type something in. You get the list of results in the middle. That's great. But to me, always the most useful part is this part on the left, where you can see the distribution across the types of documents that I've found and some other categories. In this case, languages. And we can immediately see how many documents, how many objects match, in our case repositories, fit into each of these buckets. So this is the most important exploration part. When you search for a hotel on booking.com, again an Elasticsearch user, you can immediately see like what are the ranges, what are the price ranges of the hotels in the area that you selected. And you immediately know. You don't have to read through all the records to know if there are any fancy hotels in San Francisco under $100. In case you didn't know that before, it's immediately apparent from the facets, from the results of the aggregations. So this is the first real use case, how people use aggregations and search together. You define your search, you display the aggregation so that people can narrow down the search and zero in on what they want really quickly, even if they didn't know what their options were previously. Of course, you could say that people could have written like, yeah, I'm looking for something starting with DJA, and I want it to be in Python. But what if they didn't know that Django was written in Python? Now they know. So that was one use case. The other use case is log analysis. As I said, a lot of people use Elasticsearch to store logs. We even have a product called Logstash that will actually facilitate that process. Excuse me. And also we have a product called Kibana to visualize it. And Kibana is just an in-browser JavaScript application. So all you see is actually calculated by Elasticsearch itself and just visualized by Kibana. So in this example, I'm searching through logs of an HTTP server. I have defined several categories on how to break it down. The request for PHP files, static HTML, PNG pictures, CSS, and everything. And we can either look at this is a result of a terms aggregation, or this is a date histogram with a terms aggregation inside, so the nested multidimensional aggregations. So you can immediately see and visualize, you can see that there is a weird drop here. This is something that would be very hard to just recognize from just looking at the raw data. For that, you need a visualization, and the results of the aggregations actually lend themselves very well to visualizations, especially if you can find a way how to express the multidimensional nature that the aggregations can have. With 2 dimensions, it's still fairly easy. If you add more, it gets hairy, and you need to define a good visualization to actually make use of it. And of course, in Kibana, you can just click on an individual field and just see the distribution. Again, the exploration part, where you look at the extension field, and you immediately get all the possible extensions, including some data, like how often is this extension, how rare. So this is our second use case for analyzing logs. And now wish me luck. So this one's for you. Okay, can you read it in the back? More or less, okay. Okay, you can read it, but better. For this example, I've loaded the dataset from Stack Overflow, and we're going to do some exploration to see what's actually happening. So I'm starting with a very simple query. I have a filtered query, and the only thing I'm filtering is I'm interested in questions. That's actually part of the URL up here. And I'm also interested only in documents that have been created after 2012. And I have 2 aggregations defined. I have a terms aggregation defined on the field tags that I call tags, and I have a frequency aggregation, which is of a type date histogram over the field of creation date, and the precision or the interval is month. So now I can execute this and see the results. So in total it was just 12,000 hits, and I can see the buckets. So the most common tag on programmerstackexchange.org is Java. People apparently have the most problems and questions about Java. C# is the second one, and so on and so forth. And we can see the distribution of the questions per tag. If we scroll down a little bit, we see the same for month. So nothing too surprising. We could very easily take these numbers and visualize it in some form of line to see sort of the distribution over month and to look for any spikes or maybe plot down the expected traffic as we see any trends. So that's the first part. Now let's get something a little bit more interesting. So we have the same thing, except I added one more nested aggregation. Now I'm looking for average comment count per tag. So I still have the buckets per tag. So again, you see Java on the first place, nothing has changed. But here there is one new information. There is an average over a numerical field that we have in our data, comment count. So we can see that Java has, by average, almost four comments. Any question on Stack Overflow for Java has almost 4 comments. And that was just us getting started. So in this example, we can see again we are starting with the same thing. We create buckets per tags. We are interested in the comment average per each bucket, per each tag. And then also what we are interested for per each tag is aggregating over comments. And I told you in the beginning that I modeled this, that comments are essentially the nested document with questions. So I'm saying, yeah, I want to aggregate over the nested documents. And I'm interested in top commenters, which is a terms aggregation over the field owner display name. I here use .raw because I don't want the analyzed version of the display name. I don't want the stemmed lowercase version. I want the actual full value. So I'm using .raw. And then for each of those, for each of the people who were one of the top 10 most commenters in this field, I want to see the maximum score for a comment. So when I run this, you can see that, again, nothing has changed. The most asked questions are still tagged with Java. There are still nearly 4 comments per question, which makes sense because there's 3,000 comments. And here are the top commenters. So the first person is called Gnat, and he single-handedly wrote 92 comments for questions tagged with Java. And the best comment for a question, best score for a comment that he wrote for Java was 7. And if you scroll down, you can see more people. And if you scroll even down, you can see it for different tags. We have limited ourselves to just the top 10 tags, and in each tag, only for the top 10 commenters. We could very easily just get the entire grid, the entire sort of multi-dimensional cube, and get it all at once. And if we scroll really down, we'll actually see the same for a month. It's part of the query I haven't shown because it looks very similar. And here we can see again, in February 2012, there was 768 questions with 2,529 comments, and the most active commenter was s.lot with 116 comments with the best score of 18. So with just one pass over the data, with an operation that took you cannot see that. So I'll tell you, it took 37 milliseconds to actually run this on my machine. And it's the entire data set of programmers.stackexchange.org. So this is definitely an interesting aggregation to run to see what's going on there. And one last that I have prepared is the significant terms aggregation. And also, just to make it more interesting, I also included percentiles, just to show off that we have them. And this aggregation, what it does, if I run it, is, again, we are defining things into buckets, in this case, again, per month, and you can see the result of the other aggregation, which is the trending. So sort of the significant tags that are significant for this month. So we can see that for this month it was Java, web development, permissions, interview, and you even get the number of documents that match versus the number in elsewhere, and the score, sort of the level of confidence we have in this prediction. There is a complicated mathematical model behind this, which I don't even presume to understand, but it gives you some interesting data. So again, we can see for the other month, it changes. The first, people were more interested in website performance, Java, web development, interview, and stuff like that. And this is not what were the most common terms in that bucket. These are what were the most significant compared to the other buckets. And sorry, I lost my keynote somewhere. Okay, so that's it from my part. And now, if you have any questions, I'll be more than happy to answer them. Thank you.
Yeah, thank you so much for your talk. Pretty insightful. Can you shed some practices on loading data in terms of batch? For example, we need to load data which are in the ranges of about 60 to 70 million documents, and looking forward to load them in an asynchronous manner, because how I understand, when I push a document in Elasticsearch, it waits for the response to come back from that side. So when we're doing it for 90 or 100 million documents, how can I do it in batch and in asynchronous manner, basically?
So for fast loading, there is a bulk API which allows you to bulk load the documents. Currently, our record speed that has been recorded somewhere is one customer of ours, I believe it was Verizon, broke the record at 8 gigabytes per second of indexing. So they used a Hadoop cluster to run a parallel job to actually start loading data in parallel into Elasticsearch. For that, if you already have a Hadoop cluster, we also have a Hadoop integration that will actually help you with that process. So overall, it just use bulk APIs. There are a lot of knobs that you can tweak to make the indexing faster. We're actually currently working on a blog post that should come up in the next couple of weeks that'll deal exactly with that, like how to optimize for load time.
Thanks.
Sure.
Thank you, Red. That was a very interesting talk. I have a question about the specifications that are needed for the hardware to actually run the Elasticsearch. Do you have any resources on the website about that? Like, say you want to load 100 million documents, and each of those documents about 50K, then what would be the size of the machine that you would need for that?
Okay, so the factor by which the data is expanded differs a lot on your settings and also on your data and what you want to do with the data. So, for example, by default, we'll take all the string values from your document and index them also together as sort of one artificial field that we call _all. And that's used when you don't specify a field that you're searching on, if you just want to search across everything. That's easily turned off. And there are other things like this which you can turn off. Also, if you're not interested in doing full text search, you can just index the exact values and not run an analysis. So unfortunately, there is no number I can tell you. What we recommend people is try. Like you should see a clear linear progression that should give you the ratio of the index data versus the raw data. And then whenever you tweak a setting like this, you can see a change and everything. So unfortunately, I don't have a good result.
Hi, I would like to ask how big is your index and if you're using dynamic mappings.
I'm sorry, how big is...
how big is the index in the demo example you had, and if you're using dynamic mappings?
So that's a good question. I don't know. Oh, I cannot show you anymore. So the index is approximately 200 megabytes in memory. No, 300 megabytes on disk. The raw data was like 200 megabytes. And no, I'm not using dynamic mappings. I'm using dynamic mappings for some of the fields. But for most of the fields, I cared enough that I actually created the mappings beforehand as part of the load script. Because for example, by default, all the string fields would get analyzed. So you couldn't do aggregations on them, or the aggregations would make no sense. For example, if you have a city and you have New York, and you analyze it, you will have New and York separately. So when you run aggregations, the data would make no sense whatsoever. So in those cases, you actually have to supply your own mappings. Make sense? Thank you.
Hi. My question would be about suggesters, word and phrase suggesters. And from what I understood, you need to insert them manually, isn't it? So does it mean that you need to implement it yourself, or how it really works?
No, absolutely not. So I actually have an example I can show. So you meant the phrase suggesters? So this is my Johnny Walker example. So I just indexed 3 documents with 3 different names. This is just using the dynamic mapping, so I'm not setting up anything. And then what I can do is, obviously it doesn't match anything on the phrase Johnny Walker, but if I also run the suggest, I get back the suggestion with the correct spelling. So you can see that I didn't have to set up anything. I just use it, and the only thing that I need to do is ask for a suggest with some parameters. But it's defined in query time. I haven't defined anything beforehand.
Okay. So it would work also for streets or something like that?
Yeah, absolutely.
Okay. Yeah. Thanks.
Thank you. Yeah, so if anybody else has some questions, please feel free to ask Honza offline, and we get ready for the next talk now. Thank you once again.
Thank you.